This ICFD++ video tutorial demonstrates the rapid setup of a low-speed flow about an airfoil at 6-degree angle of attack by use of the Aerospace Wizard. This tutorial will then demonstrate a second case where the Aerospace Wizard is used with the coefficient of lift driver, or CL driver, to automatically increment the angle of attack until a desired coefficient of lift is achieved. The Aerospace Wizard and CL driver are both part of the Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. Before demonstrating the setup of the first case with the Aerospace Wizard, the new features and components of the ICFD++ AUI are briefly reviewed for first-time users. A more in-depth discussion of the ICMP AUI features common across all Metacomp software can be found by clicking on the ICMP AUI demo link, which is popping up on the left side of the video. Alternately, you may refer to the ICMP AUI section of the ICFD++ documentation. The ICFD++ interface is composed of 5 main components: the menu bar, the toolbar, the canvas, the notebook panel, and the action panel. The first component, called the menu bar, is located at the top of the screen where the mouse is now moving. The menu bar is a common feature across all ICMP components and provides a traditional way of navigating to many of the tools that support CFD++. The second component, called the toolbar, provides shortcuts to the commonly used functions and visualization controls. I'm sweeping the mouse across the toolbar to highlight its location. The third component, called the canvas, is where geometry, mesh, or solution is displayed. This component typically occupies the greatest portion of the screen and is located where the mouse is now moving. The example that we will be using today consists of a 2D mesh. Typically, you would see the surface grid in the canvas panel, but for a 2D mesh, we only see the outer boundary. However, we can display the grid by using the Toggle 2D button found in the toolbar. Within the canvas, the mouse is used to control the view of the geometry or mesh. You can rotate the three-dimensional view of the geometry by moving the cursor to the canvas and then holding down the left mouse button while simultaneously moving the mouse. You can see that the 3D view changes as I move the mouse. You can also perform a two-dimensional rotation by simultaneously holding down the right mouse button and moving the mouse left or right. Moving the mouse left will result in a counterclockwise rotation, whereas moving the mouse right results in a clockwise rotation. You can zoom the view by also holding down the right mouse button, but by moving the mouse up or down. The up motion zooms in, and the down motion zooms out. Finally, the geometry can be translated or panned across the screen by holding down the middle mouse button and moving the mouse in the direction you wish to move the geometry. The fourth component of the AUI interface, called the notebook panel, shows tabs for each of the ICMP components that is active for the present simulation, and one or more information trees. The present screen shows only one notebook for CFD++, which contains the Setup Wizard action tree, the Groups and Boundary Families information tree, and the Boundary Conditions information tree. The fifth component of the AUI is called the Action Panel. The Action Panel presents the user with relevant choices that correspond to the active branch of the Setup Wizard action tree and to choices selected in previous and current branches of the Setup Wizard action tree. All of the panels are dockable and resizable to suit your preference. The current window will now be closed and a new window will be used to begin the tutorial example. The window that is now visible is the default window obtained when opening the AUI. For this example, I open the case starting from the location of the tutorial files. Therefore, the Select Working Directory defaults to the proper path. However, if you launched the AUI from another directory, you can simply click the Browse button and navigate to the location of the mesh files necessary for this tutorial. When the correct working directory has been selected, simply select OK within the Action panel to proceed. The next item of the Action panel presents us with options to analyze the grid files and to read the boundary conditions family file. Since this is the first time that we've executed the setup from this directory, both default to yes. So select those defaults, or ensure that both are clicked to yes, and press OK to proceed. A grid information panel then pops up, presenting the results of the grid analysis. In this case, there are over 36,000 quadrilaterals in this tutorial mesh, and there are two boundary selectors with the names of outer and wing. We can simply click OK to dismiss this pop-up window and are taken to the Cell Types and Volumes Action panel. This panel is auto-populated based on the results of the grid analysis, so we can simply click OK to proceed. At the General Problem Definition Action panel, we're going to leave the default option for General Fluid Problem, but we're going to select Yes to use a preset problem class wizard. In this case, we're going to use the external arrow wizard provided by the AUI. We'll click OK to be taken to the external arrow wizard itself. For this tutorial, we're going to complete our simulation using the SI units. We're going to change the type of input to be provided from the default Mach altitude input to Mach Reynolds number temperature input. We're going to change the free stream Mach number to 0.15, and we're going to change the Reynolds number to 1.76 e to the 6th. One thing to note about the Reynolds number of this problem is that this is a Reynolds number per unit meter. Now, typically, Reynolds numbers are defined with a unit length. To obtain a Reynolds number per unit meter, simply take the problem-based Reynolds number and divide by the reference length. For example, if you were simulating an airfoil with a problem-based Reynolds number of 1 million and a chord length, which was your reference length, of 2 meters, you would divide the Reynolds number of 1 million by 2 meters to get a Reynolds number per unit meter of 500,000. And that would be the value, the 500,000 would be the value that you would enter in this Reynolds number location. For this tutorial, we're going to leave the free stream temperature at the default 288 Kelvin. We're going to change the plane that the alpha angle is in to the XY plane. Now, sometimes it's easier to see this by toggling the 2D view to visualize the grid. We'll zoom in, and you can see that our airfoil here in the middle is defined in the XY plane. For this tutorial, we want to simulate an angle of attack of 6 degrees. So we're going to enter a pitch angle of 6.0. We're going to leave the yaw angle, or beta, at 0 degrees. We're going to keep the default 2-equation realizable K-epsilon turbulence model, and we're going to enter a turbulence intensity of 0.02, or 2%, and select the default turbulent to laminar viscosity ratio of 50. At this point, we could press OK to run the aerospace wizard. After a moment, an information panel pops up saying that the aerospace wizard has completed, and click OK. And we're taken to the next item in the setup wizard action tree that requires our input. Now, if we notice, many new items have been populated in the setup wizard action tree, and most of them have a green check next to them. There are just a few here that have a red X that will require additional input. So the first of those is the additional specifications action panel. For this first setup in the tutorial, we're going to keep all of the default values of no and none for the alpha beta Mach controls panel. In a later portion of the tutorial, we will revisit this panel and we'll activate the CL driver. But for this first setup, leave it at none and click OK to proceed. We're next taken to the physics source terms action panel. Again, we're going to leave this as no. Click OK to proceed. And now we're brought to the Boundary Condition Setup action panel. In this panel, we associate the boundary families with specific boundary conditions. To do that, we simply left-click on one of the boundary families to select it, and then left-click and hold and drag over top of the boundary condition that we want to associate with that boundary family. For the outer boundary, we want to associate it with an open boundary condition, so drop or release the left mouse button when the cursor is over the open boundary condition. That pops up a panel allowing us to define a new open boundary condition. We're going to keep the default inflow, outflow, primitive variable boundary condition type. We're provided with existing information sets, in this case 2 primitive variable information sets, or we could define additional ones if necessary. When we executed the Aerospace Wizard, it automatically created these first 2 primitive variable information sets, 1 and 2. Now, if we look carefully at the values associated with these 2 information sets, we see that they're identical. Now, the Aerospace Wizard sets up 2 identical primitive variable information sets with the intent that the first information set can be associated with the initial conditions. And in fact, the Aerospace Wizard has already set up the initial conditions and associated the initial conditions with the primitive variables 1 information set. It's typically intended that primitive variables 2 would be associated with the outer boundary conditions. This allows us to define slightly different properties for the initial conditions and the boundary conditions, if so desired. So in this case, we're going to select primitive variables 2 by clicking on the radio button to the left of primitive variables 2 and clicking OK to proceed. When we do this, we see a change in the boundary family's tree. Originally, there was a red X to the left of the first boundary family, such as we see here to the left of the second boundary family. That red X has now changed to a green check mark. And this indicates that the first boundary family has now been associated with a boundary condition. Now we need to associate the second boundary family, called wing, with a boundary condition. To do this, we can again click and drag by left-clicking and holding the mouse button to the wall boundary condition type. We'll release the mouse button, and a panel pops up providing wall boundary condition types. We're going to select the default viscous solve to the wall, adiabatic, and click OK to accept. At this point, both boundary families now have a green check mark next to them, indicating that they have been associated with boundary conditions, and so we can proceed by selecting OK. The next action panel requiring input is the neutral plot file options. For this panel, click the Output Options drop-down menu and go to Turbulence. We're going to activate some additional variables for output, first being the turbulent eddy viscosity, and the next being the ratio of turbulent to laminar viscosity. Select those 2 boxes, and we can scroll down, click OK to proceed. Click OK to write the neutral plot file options file. And now we're brought to the probe and output file action panel. Here we could change the rate that the solution restart files and neutral plot files are written. We could also select probes to additionally monitor the solution. For this tutorial, we're simply going to select the defaults and press OK to continue. And now we're brought to the Save Input File action panel. You can click OK to proceed. And now the input file has been saved. This tutorial case is a simple 2D geometry, which can easily run on a desktop or a laptop. To run this case interactively, you can go to the Tools menu, come down to Run CFD++, select the default double precision single CPU, and simply click Run to execute the case. This concludes the demonstration of the Aerospace Wizard setup. For information on post-processing the case, refer to the post-processing section of the tutorial page. At this point, I will stop this case, dismiss the panel, and we're going to open a new session and start the second part of the tutorial, which is a setup using the Aerospace Wizard and the CL driver. In part 2 of example 16, we're going to demonstrate the use of the Aerospace Wizard in conjunction with the coefficient of lift driver, or CL driver. The CL driver is used to automatically increment the angle of attack until a desired coefficient of lift is achieved. To begin the setup, ensure that the working directory, including the case files, have been selected. You can click Browse to navigate to the directory, and then click OK to proceed. In this case, I have opened the AOI from the same location that was used for part 1 of this video series. An mcfd.imp file already exists, but we don't want to read it. We're going to start over from scratch. So we can simply click No. We don't want to load the input file in the current directory, and then select the default Yes to analyze the grid files and to read the boundary condition family file. If you opened from a clean directory, this first question will not appear, and you'll simply be asked to analyze the grid file and to read the boundary condition family file. In that case, select Yes, and then click OK to proceed. As before, a grid information panel appears showing us the results of the grid analysis. You can simply click OK to dismiss that panel, and click OK at the cell types and volumes action panel, which has been auto-populated for us. At the General Problem Definition action panel, keep the default General Fluid Problems, and then select Yes to use a preset problem class or wizard. As before, we're going to use the external arrow wizard, and we'll click OK to proceed. We're brought back to the external arrow wizard action panel. We're going to repeat the setup from before, so we're going to switch the input type to Mach Reynolds number temperature. We're going to change the free stream Mach number to 0.15. We're going to enter a Reynolds number per unit meter of 1.76 e to the 6th. We're going to leave the default temperature of 288. We're going to change to the XY plane for the alpha angle. But in this tutorial, we're going to leave the pitch angle, or alpha, at 0. It's important when using the CL driver to start the simulation on the linear portion of the lift curve. For that reason, we recommend starting at an angle of attack of 0 and incrementing from there. We're going to also leave the yaw angle, or beta, at 0 degrees. Select the default 2-equation realizable K-epsilon turbulence model. Change the turbulence intensity to 0.02, or 2%. And leave the turbulent to laminar viscosity ratio at 50. At this point, we'll click OK. Once the wizard has completed, select OK. And again, we're brought back to the additional specification action panel. In part 1 of the tutorial, we selected the defaults for all of these options, but in this case, under the alpha beta Mach controls, we're going to click to drop down the menu, and we're going to select the CL driver and click OK. We're now brought to the physics source terms. Again, select the default No, click OK to proceed. We're back at the boundary conditions panel. We're going to repeat the setup that we used in the first video. So left click once to select the outer boundary family, then left click and hold and drag to the open boundary condition type. We're going to select the default inflow outflow boundary condition, primitive variables, and we are going to check the radio button next to primitive variables 2 information set. You can click on it to verify the values. Click OK to dismiss that panel. Next, we're going to associate the wing boundary family by left-clicking once to select, and then left-clicking and holding and dragging to the wall boundary condition type. Again, accept the default viscous solve to wall, adiabatic, and click OK to proceed. Once both boundary families have been associated with boundary conditions, we can click OK to proceed to the next item in the action tree, which is the CL driver controls action panel. For this action panel, we're going to keep the default answer of no to the question of using a user-defined subroutine. We're going to use the built-in calculation of lift for this tutorial example. We're going to accept the default boundary only for the adjustment of the velocity vectors. For this example, we're going to need to create a new fluxes, forces, and moments entry. So we'll click the new FFM entries button. To define a new entry, simply select entries and click the green plus symbol. Once we press the green plus symbol, a new entry appears. We can select that new entry, left click once to highlight it, and then click the Edit tab, which is this icon of a sheet of paper with a pencil. In the window that appears, we're going to change the entry type to coefficients. We're going to leave the entry dimensionality at dimensional. We are going to press Compute and Autofill Free Stream Reference Quantities. We're going to select the primitive variables 2, which corresponds to our outer boundary. Click Edit to see the properties if you wish. Click OK. Simply click OK after selecting the primitive variables 2 information set. You now see that the reference quantities have been set for you. For this tutorial, the chord length of our airfoil is simply 1 meter, and therefore we can leave the reference length, the reference area, and the moment center at the default values of 1 and 0. Here we would set the angle of attack corresponding to our outer boundary condition. In this case, we set up the arrow wizard with a 0-degree angle of attack, so we're going to leave the default value of 0. If we had used another angle of attack, such as a value of 6 that we had used in the first video, we would enter that same value here. But again, we set it up with a 0 angle of attack, so leave 0. Make sure that the angle of attack plane is correct. Again, in this case, the XY plane is correct. And then we need to select the boundary family that is associated with the wing or the solid boundaries. So in this case, that's boundary family 2, which is called wing. So simply click the box next to it to select it, and then click OK to exit out of this panel. You can then click OK to exit the fluxes, forces, and moments processor. We are prompted to open the fluxes, forces, and moments plotter. Since we have not run the case, there's nothing to plot, so click No. And we're brought back to the CL driver controls action panel. Now we have created the new fluxes, forces, and moments entries, but they don't appear here in the menu until we click the Load Existing Fluxes, Forces, and Moments entries. Once we do that, one entry appears with the name coefficients. So this is the entry that we just created, so simply click the radio button next to that to activate this fluxes, forces, and moments entry for our CL driver calculations. We then need to define the outer boundary information set. So this will be the boundary condition that will be modified to set the coefficient of lift. If you recall, we associated primitive variables 2 information set with the outer boundary. So click the radio button next to that. And we can scroll down to see the rest of the action panel. The CL driver operates by converging the solution to checkpoint 1. Once this iteration number is reached, the angle of attack associated with the boundary condition is altered by the angle of attack increment, and the simulation continues to checkpoint 2. The coefficient of lift is then calculated at checkpoint 1 and checkpoint 2 and used to determine the information necessary to complete the calculation. After checkpoint 2, The angle of attack is then updated at the interval set by the interval adjustments entry, in this case 50 iterations. For this example, we're going to leave the default values for the step number for checkpoint 1, 2. We're going to leave the default angle of attack increment of 1 degree, and we're going to leave the default interval adjustment at 50. For this tutorial, we're going to set the target coefficient of lift to 0.3, and we're going to keep the defaults for the minimum angle of attack, maximum angle of attack, and minimum and maximum lift slope. These inputs are simply used to bound the algorithm and to ensure convergence. At this point, we can click OK to accept the inputs, and we are brought to the neutral plot files options input. As we did in video 1, select turbulence for the output options and activate turbulent eddy viscosity and the ratio of turbulent to laminar viscosity. And scroll down and click OK to proceed, and OK to write the neutral plot files option file. At the probe and output files action panel, we'll click OK to accept the defaults. Now, before saving, we do need to make some additional modifications. For this case, we're going to scroll back up the action tree and stop at the Simulation Strategy Integration panel. Since this case is altering the boundary conditions in order to seek a coefficient of lift, we need to provide some additional steps for the run to complete. So we're going to increase the number of global time steps for this run to 1,500. We're going to leave the orders of magnitude of convergence at 5. Now, if we were to run the case with these parameters, it would stop before even the first checkpoint for the CL driver. This is a 2D case that converges very rapidly, and in fact would converge within about 150 iterations. So we're going to use some advanced convergence controls to keep that from happening. We're going to use type 1 controls, which monitor our fluxes, forces, and moments entries and ensure that they have reached convergence or have stopped changing before the simulation terminates. In this case, we only have one fluxes, forces, and moments entry, so simply select entry 1 coefficients, and we'll keep the default values for the sliding interval and the frequency to check the coefficient values. Now, even with these additional controls, the case may stop before the final coefficient of lift has been achieved. So we're also going to use some advanced controls. So we press the plus next to the advanced controls to expand the options, and we're going to set a minimum number of global steps for this run. Now, if you recall, checkpoint 1 occurred at 250 iterations, checkpoint 2 occurs at 350 iterations, and then each update occurs 50 iterations following the second update. So we want the run to complete checkpoint 1, 2, and at least a couple iterations. So we're going to set a minimum number of global steps at 500. And then we'll click OK to proceed. And we're brought back to the Save Input File action panel. Click OK to save the input file. And as before, we can go to the Tools menu, click Run CFD++, select the default double precision and the default single CPU, and simply click Run to execute this case. So that completes this setup tutorial showing the use of the Aerospace Wizard and the CL driver. For information on post-processing this case, refer to the post-processing section of the tutorial page. Thanks.